Well, the hope is you have watched the video podcasts for the Nernst equation parts 1 and 2, or this part 3 is not going to make a lot of sense to you. This is going to discuss the solution to part C of the sample problem, which asks the question, what are the equilibrium concentrations of the ions? And so that's where we're headed. Welcome. Let's look at some conditions at equilibrium that will be helpful to us. Delta G, which is Gibbs free energy, is equal to 0 at equilibrium. The forward and reverse reaction rates, or the forward and reverse reactions occur at equal rates. There's no net flow of electrons at equilibrium, so E of the cell will equal 0 volts. And at equilibrium, the value for K is equal to Q. So in order to find the concentrations of the ions at equilibrium for the cobalt 2 plus and the nickel 2 plus, we need to solve for Q first. And the good news is in part B, we learned how to solve for Q, so a lot of this will be very much review. Here's our data table. The energy of the cell at equilibrium will be 0.00 volts. The energy of the cell under standard conditions we calculated in part 1 of this Nernst equation podcast series at 0.04 volts. N is equal to 2 moles of electrons. We need to solve for Q. Our initial concentrations of nickel 2 plus and cobalt 2 plus are 0.80 moles per liter and 0.20 moles per liter respectively. And our final concentration of nickel 2 plus and our cobalt 2 plus are what we're going to find at the end of the problem. But we have to solve for Q first. So to solve for Q, we begin our series of rearrangement processes with this equation. So the first thing we're going to do is add the expression 0.0592 volts divided by n times the log of Q to both sides. So we'll have E of the cell plus 0.0592 volts over n times the log of Q is equal to E0 of the cell, which is better known as the energy of the cell under standard conditions. Continuing my rearrangement process, I subtract the energy of the cell from both sides, so that on the left side of the equation I have 0.0592 volts divided by n times the log of Q is equal to the energy of the cell under standard conditions minus the energy of the cell, in this case at equilibrium. Continuing our rearrangement to solve for Q, I'm going to divide both sides of the equation by the expression 0.0592 volts over n. When I do that, it cancels on the left-hand side, and I'm left with the log of Q is equal to the E0 of the cell minus E of the cell, or the standard energy of the cell, or the energy of the cell under standard conditions, minus E of the cell divided by the expression 0.0592 volts over n. I now take 10 to both sides of the equation so that I can get rid of the logarithmic expression on the left-hand side and isolate Q. So Q is equal to 10 raised to the standard energy of the cell minus the energy of the cell at equilibrium divided by the quantity 0.0592 volts over n. And now I'm going to substitute in my values and solve for Q. So 10 raised to the power of 0.04 volts minus 0 volts divided by the quantity of 0.0592 volts divided by 2 is equal to 22. And I'll just kind of broaden this out. That expression 0.04 volts minus 0 volts divided by the quantity 0.0592 volts divided by 2 gives us an exponent of 1.35. So Q is equal to 10 raised to the power of 1.35, which is equal to 22. So our value of Q is 22. Well, the good news is that at equilibrium, Q is equal to K. So we know that our value of K is equal to 22. Since we know K, we can now solve for the equilibrium concentrations. Here I set up a BCA chart. Actually, in reality, it probably should just be an ICE chart, but They will do the same thing for our purposes. We know that K is equal to 22. So we know that for the nickel, it starts out at 0.80 moles per liter. It's going to change by an amount X. And after we reach equilibrium, it will be 0.80 moles per liter minus X. The cobalt will be 0.20 moles per liter plus X. So our equilibrium constant expression K is equal to 22, is equal to the molar concentration of the cobalt 2 plus ion over the molar concentration of the nickel 2 plus ion. So it's equal to 0.20 plus X divided by 0.80 minus X. And in keeping with my love of this slide, you get to see it a second time. So hopefully you've caught up and you understand where we are. If not, you may want to just stop the podcast here and move it back to the beginning and work through this step by step until you get to this slide and see that you have an understanding of what we're about to do. We're going to go through the process of solving for X. So 22 times 0.80 minus X is equal to 0.20 plus X. 17.6 minus 22X is equal to 0.20 plus X. I subtract 0.20 from both sides and I add 22X to both sides. So I get 17.6 minus 0.20 is equal to X plus 22X. This is our never-ending goal to get the X's on one side of the equation and our non-X terms on the other side of the equation. Since 17.6 is equal to 23X, X is equal to 17.6 divided by 23, which gives our X value to be 0.765 moles per liter. And now at last, we can find our equilibrium concentrations. The final concentration of the cobalt 2 plus is going to be equal to 0.20 plus 0.765, and that gives us a final concentration of cobalt 2 plus of 0.97 moles per liter. Our concentration of nickel 2 plus ion is equal to 0.80 minus 0.765, and that is then 0.04 moles per liter. So those are our final concentrations. If this is still a mystery to you, rewatch this series starting with part 1 of the Nernst equation video podcast. Go through this slowly, methodically. If you're still struggling, please see your instructor because this is a very critical part of calculations involving voltaic cells. Well, this is the end of part 3 of our series on applying the Nernst equation to calculations involving voltaic cells. And I want to leave you with one more quote from Benjamin Disraeli, great British statesman. "Fame and power are the objects of all men. Even their partial fruition is gained by very few, and that too at the expense of social pleasure, health, conscience, and life." I wish you well.